Hello friends, today I shall be talking on odds ratio, an important concept and confusing concept in data science, biostatistics, statistics in many areas. Odds ratio is easy to define, but the way it is used sometimes in many cases confuses us. Let us start with log odds in logistic regression. So to talk about logistic regression, it's a binary classifier. Our target variable y has two classes, one which denotes success and 0 which denotes failure. Let p denote the probability of success and subsequently 1 minus p denote the probability of failure. The log odds is modeled in logistic regression as log of p by 1 minus p, which is the linear sum of the weights and the parameters beta 0 plus beta 1 x1 plus beta 2 x2 etc. plus beta n x2. So this is linear and we equate it to log odds, probability of success by probability of failure. This p by 1 minus p is known as the odds ratio, the ratio of the probability of success to probability of failure. The log odds being greater than, less than or equal to 0 has clear implications. When log odds is less than 0, the probability of success is less than probability of failure. When log odds is greater than 0, probability of success is more than probability of failure, and in case of them being equal, the odds ratio is 1, p by 1 minus p, and the log odds is 0. So that's the definition of odds ratio. We can talk about some intuition behind odds ratio. If we flip an unbiased coin, the probability of getting heads and probability of getting tails are equal, both 50%. Imagine we get a biased coin that makes it 2 times more likely to get heads. But what does twice as likely mean in terms of the probability? It cannot literally mean to double the original probability value, because doubling 50% would yield 10%. Rather, it is the odds that are doubling from 1:1 odds to 2:1 odds. The new probabilities will be 66 plus 2/3% for heads and 33 plus 1/3% for tails. So that is the use of odds ratio. That's the story behind the intuition of the odds ratio. We can talk of statistical intelligence in terms of odds ratio. In a 2 by 2 contingency table, x and y are independent. Their joint probabilities can be expressed in terms of the marginal probabilities as follows. So this is sum of the first row is probability x equal to 1, sum of the second row is probability of x equal to 0, sum of the first column is probability y equal to 1, sum of the second column is probability y equal to 0. In this case, the odds ratio equals 1. And conversely, the odds ratio can only equal 1 if the joint probabilities can be factored in the way, that is, probability of x equal to I, y equal to j equal to probability of x equal to I times probability of x equal to j. So that's the definition of independence, and only in case of independence the odds ratio is 1. Thus the odds ratio equals 1 even only if x and y are independent. So that comes from the concept of statistical intelligence. We can talk about statistical inference. We can use the odds ratio, log odds, as an estimator, a statistics, a variable, and the distribution of that is approximately normal with log odds ratio sigma square, where standard error is given by root over 1 by n11, 1 by n10, 1 by 01, 1 by n00, where n11, n10, n01, n00 are the cell frequencies of the 2 by 2 contingency table. In many cases, in terms of accuracy calculation, or in case of developing the confusion matrix, we need this 2 by 2 contingency table. Now, the confusing part, we have relative risk against the odds ratio. So we have, if we plot risk ratio in the x-axis, odds ratio on the y-axis, when baseline equal to 0.01, we get more or less a straight line. When the baseline risk is 0.5, we get a parabolic line. It's plotting risk ratio versus odds ratio. Relative risk is usually better than odds ratio for understanding the relation between risk and some variables such as radiation of a new drug. That also explains if the rare disease assumption holds. Rare disease assumption means the data is imbalanced, then the probability of true cases is very low. The frequency of true cases is very low against the frequency of false cases. So that data is imbalanced, and in that case only the odds ratio is a good approximation to the relative risk. That is that, and that it has some advantages over relative risk. When the rare disease assumption does not hold, the unadjusted odds ratio will be greater than the relative risk, but novel methods can easily use the same data to estimate relative risk, risk difference, best probabilities, and all other quantities. We need to be careful when using odds ratio or when using relative risk. So relative risk is approximately odds ratio by 1 minus RC plus RC into odds ratio, where RC is absolute risk of the unexposed group, the control group risk. Confusion and exaggeration. Odds ratio have been confused with relative risk in medical literature. For non-statisticians, the odds ratio is a difficult concept to comprehend, and it gives a more impressive figure for the effect. However, most authors consider that relative risk is readily understood. In one study, members of a national disease foundation were actually 3.5 times more likely than the non-members to have heard of a common treatment for the disease, but the odds ratio was 24, and the paper stated that members were more than 20-fold more likely to have heard of the treatment. A study of papers published in 2 journals reported that 26% of the articles that used an odds ratio interpreted it as a risk ratio. Even in the papers, we are seeing these mistakes, the confusion between odds ratio and the relative risk. The entire article is based on this online blog. I'll stop here. Thank you. Like, comment, share, and subscribe my videos. I am available for one-to-one sessions too. Thank you.